in today's lecture, we're going to study chapter 10, stresses in the soil mass. If you look at our course objectives, this is actually the last major course objective. That is to determine stress changes, specifically vertical stress changes in soils due to foundation loads at the surface. So we basically put a check mark on all the other course objectives by now. In terms of what we're going to do in this chapter, so for today's lecture, I'm going to introduce this vertical stress distribution, this concept of stress distribution. And then to solve stress increase due to surface loads, due to your foundation loads, there are two groups of solutions we can use. One is by Bushinek, and so that's what we're going to discuss today. And so Bushinek basically developed a solution for point load due to develop solutions for stress increase due to point load, and which are then integrated to get stress increase due to other shapes of distributed loads. So that's Bushinek solution. And then also Westergaard solution are another common group of methods. We can use Westergaard solution to determine stress increase as well. So that's the final part of this chapter. So for today, we're going to start with Bushinek solution. And before that, I want to introduce this concept of stress distribution. So what we are dealing with in this chapter. So I have some issues with the slides again. Hold on one sec. Okay, all right. So first, what is stress distribution? So what are we trying to do here in this chapter? So I'm going to present two scenarios here to illustrate this stress distribution problem. Scenario one here. If you look at this figure, we have two soil layers. One is dense sand on top, and there's normally consolidated clay, which we know is soft and tends to induce large consolidation if they're loaded. In chapter 11, you learn how to calculate stress increase if you put some very large sandy fields. So very large, I put infinite long sandy fields. So basically the entire field is compressed by this sandy field on top. In chapter 11, we learned how to calculate the consolidation settlement in the clay layer due to this added sandy field. And if you recall how we do the consolidation calculation, so one key value or one key quantity we need to calculate is the stress increase in your consolidating layer, in this case, clay layer. For that very large sandy field, this is basically a 1D compression assumption. So basically the entire soil layer is compressed in the vertical direction. It's 1D compression. And it's pretty straightforward to calculate the vertical stress increase we call delta sigma z in the clay layer. And if, let's say, we assume there's 10 feet of sandy field to be added, and we know the unit weight of the sandy field is 100 PCF, then delta sigma z is simply the height of the sandy field, 10, times the unit weight of the sandy field, 100. So that gives us 1000 PSF. Okay. And because we assume this is very large sandy field, it's 1D compression. So delta sigma z is the same everywhere in the normally consolidated clay layer. So the increase of vertical stress is 1000 PSF. And with this increase in vertical stress, then we can calculate the consolidation settlement using what we learned in chapter 11. So that's scenario one. The second scenario, again, we have this sand layer and clay layer here. So dense sand on top, NC clay at the bottom. And then instead of that 1D, that very large sandy field, let's consider a finite area. So we have this 10-story building that has this finite area of contact, this footing right here. And the pressure from this 10-story building to your clay or to your soil layer Q is 1000 psf. So that's your surface pressure Q, 1000 pound per square foot. And then you're asked to, so let's estimate the vertical stress increase in clay layer, delta sigma z here. So what would delta sigma z be in this case? Okay. So this is clearly different from that sandy field, that 1D compression. And if you are, so the value of this vertical stress increase really depends on where you look. So if you're really close to the center of this footing, to this building, close to the surface, so you're going to get increase of vertical stress delta sigma z probably closer to that 1000 psf at the surface. So if you're close to that footing, you're probably going to get 1000 or very close to 1000 psf. But if you move further away, so if you calculate stress increase, some depths down below or at some distance down below, you're going to get the different stress values. And this is due to that finite loading area at the surface. And this is basically what we're going to discuss in this chapter. And we're going to basically calculate the distribution of this vertical stress increase in the soil layer due to a finite area distributed loading at the surface. And to calculate the stress distribution due to that surface loads, there are actually different methods you can choose. The first one is called load spread method. So this is the simplest approach, and it's also called the 2-to-1 method. So this method basically assumes that the area over which the load acts increases in a symmetric way with depth. And I have a figure to illustrate this. And so with this assumption, at a particular depth, you can actually calculate the enlarged area of that footing. So basically over which area that load spreads at a certain depth. So as I mentioned, this method is pretty fast. It's very simple, but because of this very simplified assumption, this method is not as accurate, but it's a quick way to estimate stress increase at certain depths. And this is a diagram illustrating this 2-to-1 method. So you have a square footing at the surface. The width of that footing is B, and the length of that footing, that loaded area is L. So length is into the paper here. So basically you have the length dimension into the paper. You have a square shape area here, and that length, this is L. And the surface pressure here, so it's Q is really surface pressure. We call Q. According to this 2-to-1 method, this area basically increases in a symmetric fashion. If you look at both sides of this footing, so that area increases with depth, and the slope of that increase is 1/2. So at the depth Z, the area over which that load acts is basically, if you use this 1/2 ratio, so you have Z/2 on one side, Z/2 on the other, and then B in the middle. So that's the area of that surface load over which, this is the area over which that surface load acts in depth Z. So for this rectangular load case, the total load is surface pressure times the area at the surface. So this is basically the total load. Let's say the load of your foundation or the load of that building is surface pressure times the surface area. And this equals to the pressure at depth Z times area over which that pressure acts at depth Z. So based on this 2-to-1 assumption, that area is B plus Z times L plus Z. So then use this, you can calculate stress increase delta sigma Z at depth Z here. So this is a very, very simple method. You can see it's just use that 2-to-1 ratio to approximate the area at depth Z, then use the equivalent of total load to calculate delta sigma Z. So that's the first method. So this method is very fast, very simple, but as I mentioned, it's not as accurate. In the second method or second group of methods you can use are advanced numerical methods. And examples of advanced numerical methods include finite element method, finite difference method. And I'm going to show a couple of figures, examples of this finite element method. But these advanced numerical methods, they are, compared to the first one, they're more accurate. And they provide a more comprehensive picture of the soil's response. So these methods provide you not only vertical stress, but also horizontal stress, deformations, and pore pressure. But the drawback of these advanced methods are they are very complicated and they're less efficient. So you need to run on computers and it takes time to get results. So here are just one example of this is a circular footing modeled by three-dimensional finite element method. So the green block here is basically the soil. And then you have that circular footing at the surface. So this is from one of the recent work or previous work we did. As I mentioned, this method gives you a more comprehensive picture of soil's response. You get not only pressure, stress distribution, but also deformations in all directions. But this method is very complicated. And the third method that's actually we're going to focus in this chapter, in this class, is analytical solutions based on theory of elasticity. Okay. So there are basically two solutions we're going to look at, as I mentioned. One is Bushy-Neck solution, and the other one is Westergaard solutions. And both of them are based on theory of elasticity. And these analytical methods basically strike a balance between accuracy and also practicality of your method. So you can, if you, we'll discuss this more in details, but all the solutions are actually presented in terms of tables and figures. So it's actually very easy to use for practical problems. The assumptions, this is for Bushy-Neck solution assumption that soils are isotropic, homogeneous, and elastic media. And Westergaard uses a slightly different set of assumptions, but they're all for elastic media. So we're going to look at these analytical solutions in more details in this chapter. And we'll start with the Bushy-Neck solution.